Hello there, and welcome to the SleepFast Science Channel. Tonight, we are going to drift into the unknown, into the questions science still has not solved. For all the discoveries we have made, the universe remains full of puzzles, paradoxes, and quiet mysteries that no one can fully explain. Some are cosmic, stretching across galaxies and black holes. Others are here on Earth, in the oceans, the atmosphere, and even inside our own bodies. These unanswered questions remind us that science is not a book of final truths, but an endless story still being written. Every mystery opens a doorway to wonder, a reminder that we are explorers in a universe far larger than we can yet understand. If you enjoy drifting off to scientific wonders, feel free to like and subscribe, or simply share your thoughts in the comments below. It helps others find their way here too. But for now, let these questions carry you. And if you are ready, let's begin. We still do not know why the universe exists at all. It seems like the most basic question imaginable. Why is there something rather than nothing? And yet science has no answer. Physics can describe how the universe behaves once it exists. Cosmology can trace events back to the Big Bang. But why there is a universe at all, why there are laws that allow it to exist, remains unsolved. Quantum physics suggests that what we call nothing is not truly empty. Even the vacuum of space teems with activity, fleeting particles that flicker into existence before vanishing again. Some physicists suggest that the universe itself may have arisen in much the same way, that absolute nothingness is unstable and something must always emerge. Others argue that perhaps our universe is only one of countless universes in a vast multiverse, each coming into being with its own laws. But if that is true, we are only pushed back to a deeper question. Why should the multiverse itself exist? Philosophers sometimes suggest that existence is simply the natural state, that non-existence is impossible. Perhaps reality, in some form, must always be. But these are ideas we cannot test. No telescope, no particle collider can measure why there is being instead of nothing. Every other question in science rests upon this one. Every star in the sky, every atom in your body, every law of nature, all exist on a foundation we cannot explain. The fact that reality is here at all remains the deepest mystery we face. The spark that set the cosmos in motion is still a mystery. We can trace the story of the universe back nearly 14 billion years to a time when it was a hot, dense fireball. We call this beginning the Big Bang. But what actually caused it? That remains unknown. Cosmologists have pieced together a detailed history from the moment the universe was only fractions of a second old. In that first instant, a rapid expansion called inflation may have blown space itself wide open. But what triggered inflation? Why did it begin? And why did it stop? These questions remain unanswered. Some theories imagine the Big Bang as a quantum fluctuation, a tremor in the fabric of reality that gave rise to space and time themselves. Others suggest that the Big Bang was not the first event, but only one moment in a cycle of births and deaths, with universes expanding, collapsing, and beginning again. What complicates the question even further is time itself. If the universe includes the birth of time, then asking what came before may not even make sense. Our instruments, the Hubble Space Telescope, the Planck satellite, and the James Webb, give us snapshots of the infant universe. But none can peer into the first instant itself. We know the universe began. We can measure its age, chart its growth, and study its afterglow. But the spark that set the cosmos in motion, the true first cause, is a mystery still hidden in the dark. Time always moves forward, but no one can fully explain why. Every moment, the present slips into the past. We remember yesterday, but not tomorrow. A broken glass never leaps back together. Heat moves from hot coffee into the air, but never the reverse. Time in our experience only flows one way. This is called the arrow of time. What makes it so strange is that the fundamental laws of physics do not require it. At the smallest scales, particles can move forward or backward in time with equal consistency. The equations are symmetrical. Nothing in them demands that time should only advance. And yet, our entire world depends on this one-way street. Scientists often connect the arrow of time to entropy, the tendency for disorder to increase. The universe began in an exceptionally ordered state and has been running down ever since. But why did it begin that way? Why should the cosmos have started in such a low entropy condition that time could even have a direction? Some physicists think the arrow of time might emerge from the way information spreads. Others suggest it is tied to the expansion of the universe itself. But none of these explanations are complete. Time's direction is something we live inside every second of our lives. And yet, why it flows forward, and only forward, remains one of the most haunting mysteries in science. Most of the universe is made of something we cannot see. When astronomers measure the way galaxies spin, they find something strange. Stars near the edges move far too quickly, as if held by an invisible force. By all logic, those stars should drift away into space. Instead, they remain bound. The conclusion is hard to escape. Most of the mass in the universe is not visible to us. We call it dark matter. Dark matter neither glows nor absorbs light. Telescopes cannot see it directly, yet we know it must be there because its gravity shapes everything around it. It holds galaxies together, bends the paths of starlight from distant clusters, and leaves faint ripples in the pattern of the cosmic web. So what is it? Scientists have searched for decades. Some think it is made of undiscovered particles, perhaps WIMPs, or weakly interacting massive particles. Others suggest axions, ghostly particles that barely interact with ordinary matter. There are even theories that dark matter could be black holes formed in the earliest moments after the Big Bang. Despite enormous effort, we still do not know. Experiments buried deep underground wait for a passing dark matter particle to collide with a single atom. So far, none have. For now, this hidden mass, 5 times more abundant than ordinary matter, remains one of the universe's greatest unsolved mysteries. An invisible force is stretching space apart faster and faster. In the 1990s, astronomers studying distant supernovae expected to find the universe's expansion slowing down. After all, gravity should be pulling galaxies back together. Instead, they discovered the opposite. The universe is not only expanding, it is accelerating. This means some unknown energy is embedded in space itself, pushing galaxies away from one another at ever-increasing speeds. We call it dark energy, though the name is only a placeholder for our ignorance. Dark energy makes up nearly 70% of the entire cosmos, yet we do not know what it is. One idea is that it is a property of the vacuum, a kind of constant energy present in empty space. Another possibility is that it points to new physics, perhaps a dynamic field that changes over time. Some theories even suggest it could be a sign that our understanding of gravity itself is incomplete. What makes the mystery even more unsettling is its consequence. The fate of the universe depends on this invisible force. If dark energy remains constant, galaxies will drift farther and farther apart until only empty space is left. If it grows stronger, it could eventually tear apart galaxies, stars, and even atoms. We can measure its effects, but we cannot see its true nature. Dark energy is the unseen hand shaping the ultimate future of the universe. The laws of physics seem tuned for life in ways we do not understand. The universe appears balanced on a knife's edge. If gravity were slightly stronger, stars would collapse too quickly. If it were weaker, galaxies might never form. If the electromagnetic force were different by even a fraction, atoms would not bind together. Even the tiniest changes in the constants of physics could erase the possibility of life altogether. This puzzle is known as the fine-tuning problem. Why should the laws of nature have exactly the values they do? There is no obvious reason for gravity, electromagnetism, or the nuclear forces to take the strengths they have. And yet, if they were different by even a little, our universe would be lifeless. Some argue this is coincidence. Others suggest that countless universes exist, each with different laws, and we simply live in the rare one where life is possible, a cosmic lottery win. Another idea is that there may be a deeper principle, still undiscovered, that forces the laws to take these exact values. For now, we cannot say. But when we look around at stars, planets, and the fact that we can even ask this question, we are reminded that the universe feels improbably, uncannily suited for life. And why that is so remains one of science's greatest mysteries. No one knows whether the universe goes on forever or ends somewhere. The observable universe is vast, about 90 billion light-years across, but we cannot see beyond it. Light has only had so much time to travel since the Big Bang, and so there is a horizon we cannot look past. But what lies beyond that edge? One possibility is that the universe is infinite, stretching endlessly in all directions with no boundary at all. If so, then space may contain an unending number of galaxies, stars, and perhaps even other Earth-like worlds. Another possibility is that the universe is finite but unbounded, like the surface of a sphere. In such a universe, if you could travel far enough in one direction, you might eventually return to your starting point. Scientists search for answers in the cosmic microwave background, the faint afterglow of the Big Bang. Its patterns might reveal the universe's shape. So far, the evidence suggests that the universe is very nearly flat, but this does not settle the question of whether it is infinite. For now, we do not know if the cosmos stretches without end or loops back on itself. The true size and shape of the universe remain hidden, just beyond our reach. Beyond the horizon of what we can see, there may be endless unknowns. When we look into space, we are also looking into the past. The most distant galaxies we can see are sending us light that has traveled for over 13 billion years. But beyond that lies a region forever hidden, the unobservable universe. This cosmic horizon is not like a physical wall. It is a limit set by the age of the universe and the speed of light. Beyond it, reality continues, but we can never know exactly what is there. Perhaps it is much the same. Galaxies, stars, and planets stretching far beyond our sight. Or perhaps it is radically different, with regions governed by different conditions or even different physical laws. Some theories of inflation, the rapid expansion thought to have occurred right after the Big Bang, suggest that our observable patch is only one bubble in a much larger reality. If true, the vast majority of the universe lies forever beyond what we can measure. We are bound within a cosmic island. The sky we see is only the smallest fraction of what may exist. The rest of the universe is out there, silent and unreachable, a permanent unknown. Some scientists believe there are other universes, but we cannot prove it. The idea of the multiverse is one of the boldest in modern science. it suggests that our universe may not be unique, but one of countless others. Each universe could have different laws of physics, different histories, even different numbers of dimensions. The concept arises naturally in some theories. Inflation may create bubble universes, each budding off with its own conditions. String theory predicts a vast landscape of possible realities. In these scenarios, our universe is simply one outcome among many. This could even help explain fine-tuning. We live in a universe suited for life because only in such universes can observers exist. But there is a problem. If other universes exist beyond our cosmic horizon, we may never be able to observe them. No light or signal could ever cross that boundary. This makes the multiverse both fascinating and controversial. It stretches the definition of science because an idea we cannot test may never become more than speculation. Still, the possibility that reality is larger than our universe, perhaps infinitely larger, is one of the most intriguing mysteries in physics. Space and time may be woven from deeper rules we have not yet discovered. Einstein's general relativity shows us that space and time are not fixed backdrops, but flexible and dynamic. They bend, curve, and stretch, shaping the paths of planets and the flow of light. But at the deepest level, what is this fabric actually made of? At the smallest scales, relativity and quantum mechanics clash. In relativity, space and time seem smooth, but quantum theory suggests that everything should be grainy, fluctuating, and uncertain. Reconciling these two views is one of the greatest challenges in science. Some ideas suggest that space and time are not fundamental at all. Instead, they may emerge from something deeper, perhaps a network of quantum information or patterns of entanglement that give rise to geometry. In this picture, what we call space-time is like a surface, and beneath it lies a more basic reality we cannot yet see. Others wonder whether time itself is even real, or whether it is an illusion created by deeper processes. If so, our most basic intuition about reality would be wrong. Space and time feel like the stage on which the universe unfolds. Yet the stage itself may not be what it seems. What they truly are remains one of the most profound unanswered questions in science. A single particle can be in two places at once, and we still do not know how. Quantum mechanics tells us that particles do not have definite positions until we measure them. Instead, they exist in a superposition, a kind of probability cloud in which many outcomes are possible at once. An electron can be here and there, passing through both slits of an experiment simultaneously, interfering with itself like a wave. Only when we look does the particle choose a place. This is not just theory. Experiments have shown superposition at work, not only with electrons, but with molecules thousands of times larger. Physicists can even create delicate states in which objects exist in overlapping possibilities. And yet no one truly understands what it means. Does the particle physically exist in two places? Or is superposition only a reflection of our incomplete knowledge? Some interpretations suggest that multiple realities split, one where the particle lands here, another where it lands there. Others suggest that reality itself is fuzzy until it is measured. Whatever the case, the ability of a single particle to seemingly exist in two places at once remains one of the strangest and most unsettling mysteries of modern science. Entangled particles echo each other across light years, defying explanation. When two particles become entangled, their properties are linked in a way that seems to ignore distance. Measure one, and you instantly know the state of the other, no matter how far apart they are. Einstein called this spooky action at a distance because it seemed to violate the cosmic speed limit. Nothing should move faster than light. Yet experiments confirm that entanglement is real. Photons, electrons, and even small groups of atoms have been entangled and separated by kilometers. No signal appears to pass between them, but the correlations remain perfect. It is as though nature itself keeps a hidden ledger, ensuring that the outcomes stay in sync. What does this mean? Some physicists suggest that reality is non-local, that the universe is woven together more deeply than space and time allow us to imagine. Others think entanglement may point to hidden variables we have not yet discovered. Still others propose that information itself may be the foundation of reality. We use entanglement in quantum computing and secure communication, yet we still cannot say why it works. The universe whispers across distance, and we do not yet know how. No one knows why observing something seems to change what it is. One of the strangest discoveries in physics is that the act of measurement affects the system being measured. In the famous double-slit experiment, particles behave like waves when no one is looking, creating interference patterns on the screen. But if we measure which slit a particle goes through, the wave-like behavior vanishes. The outcome changes simply because we observed it. Why should this be? One explanation is that the wave function, the mathematical description of all possible states, collapses into a definite outcome when observed. But what counts as an observer? Is it a measuring device, a human consciousness, or is collapse only an illusion hiding deeper laws we do not yet see? Some interpretations say every possibility happens, branching into multiple universes. Others suggest that particles only appear definite when information about them becomes irreversible. None of these ideas have been proven. What we do know is that the line between observer and observed is not as simple as we once believed. The universe seems to care whether it is being watched, and no one knows why. Gravity is far weaker than every other force, and we do not know why. Gravity rules the cosmos. It holds planets in orbit, shapes galaxies, and governs the motion of stars. And yet, compared to the other forces of nature, it is unbelievably weak. A small magnet on your refrigerator can easily overcome the pull of the entire Earth. Why is this? The electromagnetic force, the strong nuclear force, and the weak nuclear force all operate on tiny scales with enormous power. Gravity, by comparison, is feeble. Physicists have tried to explain this hierarchy problem for decades. One possibility is that gravity spreads into hidden dimensions we cannot see, diluting its strength. Another is that the true scale of gravity is strong, but it is masked by unknown physics at small distances. Despite centuries of study, we still do not understand why gravity is so much weaker than the other forces. This imbalance is not just a curiosity. It is fundamental to the structure of the universe. Without it, stars and galaxies could not exist. The weakness of gravity is the quiet mystery that makes the cosmos possible. Einstein's universe and the quantum world both work, yet they refuse to fit together. General relativity describes the large-scale universe with unmatched precision. Quantum mechanics explains the microscopic world with astonishing accuracy. Each theory has been tested to extremes, and both pass every experiment we can throw at them. But they do not agree with one another. When we try to describe situations where both matter and gravity are quantum, like inside black holes or in the first moments of the universe, the equations break down. Infinity piles upon infinity. The two frameworks are mathematically incompatible. Physicists have searched for decades for a theory of everything that unites them. Candidates like string theory and loop quantum gravity offer tantalizing possibilities, but no experiment has confirmed them. Without a unifying theory, we cannot truly understand the birth of the cosmos or the nature of spacetime at the smallest scales. The fact that our two most successful theories seem to describe different realities is one of the greatest paradoxes in science. Both work perfectly, and yet together they fail. The true heart of a black hole remains unknowable. Black holes are regions where gravity is so strong that nothing, not even light, can escape. As matter falls inward, it is crushed toward the center. According to Einstein's equations, everything collapses into a single point of infinite density, a singularity. But infinity is usually a sign that our mathematics has failed. What truly lies at the heart of a black hole? Some think the singularity is real, a place where the known laws of physics break down. Others believe a deeper theory, perhaps quantum gravity, will replace the singularity with something else, a loop of spacetime, a finite core, or an entirely new kind of object hidden inside. The event horizon conceals the interior completely from view. For now, the heart of a black hole is sealed away beyond observation and beyond certainty. It remains one of the most inaccessible mysteries in all of science. We still do not understand what singularities really are. A singularity is a place where our equations predict infinities, density without limit, curvature without bound, time and space collapsing into something beyond definition. Black holes contain them. The Big Bang may have begun with one, but what are they really? Are singularities actual features of nature, or are they signs that our theories are incomplete? Many physicists believe they point to the limits of Einstein's relativity. Somewhere beyond that limit, a new theory, one that merges relativity with quantum mechanics, must take over. In such a theory, the infinities might dissolve into something finite and describable. Until then, singularities remain puzzles at the edge of physics. They are places where our understanding stops and our models break apart. What lies beyond them is hidden, waiting for a deeper theory of reality. Whether information vanishes inside a black hole is still an open question. When matter falls into a black hole, it seems to disappear forever. But in physics, information, the details about the state of a system, is supposed to be preserved. So what happens to the information locked inside a black hole? Stephen Hawking showed that black holes can slowly evaporate through radiation. But if they vanish completely, where does the information go? If it is destroyed, the laws of quantum mechanics would be violated. If it escapes, then somehow the information must leak out through the Hawking radiation, a process no one fully understands. This puzzle, known as the black hole information paradox, has challenged physicists for decades. Some think the information is stored on the event horizon itself. Others argue that black holes might connect to other regions of spacetime, allowing the information to escape. Still others think our understanding of quantum mechanics itself may need revision. The fate of information in a black hole is one of the most important open questions in physics. It touches not only on black holes, but on the deepest foundations of reality. Hawking radiation is predicted, but no one has ever seen it. In the 1970s, Stephen Hawking made a stunning prediction. Black holes are not truly black. Quantum effects near the event horizon should cause them to emit faint radiation, slowly losing mass over unimaginable timescales. Eventually, they could evaporate completely. This radiation, now called Hawking radiation, is one of the most famous predictions in modern physics. Yet we have never observed it. Real black holes are surrounded by hot gas and violent environments that overwhelm the faint trickle of radiation. Detecting it directly may be impossible with current technology. Still, the idea has enormous consequences. It ties together quantum theory, relativity, and thermodynamics. It suggests that black holes have a temperature and that space-time itself is more dynamic than we once realized. Laboratory experiments have tried to create analogs of Hawking radiation using sound waves and fluids, but these remain indirect hints. Whether Hawking radiation truly exists is still unproven. If it does, it will reshape our understanding of black holes. If it does not, something even stranger must be happening at the edge of space-time. Black holes may even be doorways to other worlds we do not yet know. Black holes push physics to its limits. Inside them, space and time bend in ways we cannot fully describe. Some solutions to Einstein's equations suggest that black holes could connect to other regions of space-time, tunnels known as wormholes. In theory, entering a black hole might lead somewhere else, but this remains speculation. Wormholes, if they exist, may be unstable. The intense gravity of a black hole might destroy anything that tries to pass through. And yet, the mathematics leaves the possibility open. Some physicists suggest that the singularity at a black hole's center could mark a bridge to a new universe with its own space and time. Others think black holes might recycle information, seeding the birth of new cosmic regions. For now, we cannot test these ideas. No signal can escape a black hole's interior, and so its secrets remain hidden. Still, the idea that black holes may be more than cosmic graves, that they could be gateways to something beyond, is one of the most tantalizing mysteries of all. We still cannot fully explain how the very first stars were born. When the universe was new, it was a dark, simple place. There were no galaxies, no planets, no metals, and no complex chemistry. Only clouds of hydrogen and helium drifted through the expanding cosmos. At some point, those clouds collapsed to form the first stars, ending the cosmic dark ages and lighting the universe for the first time. But exactly how this happened remains a mystery. These first stars, called population 3 stars, would have been enormous, perhaps hundreds of times the mass of our Sun, burning hot and bright, but living only for a few million years before exploding as powerful supernovae. They seeded the cosmos with the first heavier elements, paving the way for later generations of stars and eventually for life. The problem is that we have never seen one. No population 3 star has ever been observed. They lived and died so quickly and so long ago that direct evidence is missing. Astronomers look for indirect clues in the chemical fingerprints of ancient stars, hoping to find hints of their violent births. The James Webb Space Telescope may finally glimpse their light. But for now, the exact process that sparked the first stars remains one of the great open questions in astronomy. Some galaxies formed supermassive black holes far too quickly. At the heart of nearly every galaxy lies a supermassive black hole, millions or billions of times more massive than our Sun. We know how black holes can grow by swallowing gas, stars, and even other black holes. But in the early universe, we see black holes that grew far too large, far too fast. Some of these giants already existed less than 1 billion years after the Big Bang. According to our models, there simply was not enough time for them to grow so big through ordinary processes. This leaves us with a puzzle. Did they form from the collapse of enormous primordial clouds, skipping the small steps entirely? Did they grow from the deaths of massive first-generation stars that collapsed into black holes much larger than we expect? Or is there a mechanism we have not discovered yet, allowing them to feed and expand at astonishing rates? These ancient black holes challenge our understanding of galaxy evolution. If we can solve their mystery, we may unlock the story of how galaxies themselves came to be. For now, they remain cosmic enigmas, giants that should not exist so soon after the universe began. No one knows why so many galaxies take on spiral shapes. When we imagine galaxies, we often picture elegant spirals, sweeping arms of stars curling outward like cosmic pinwheels. The Milky Way is one of them. But why should galaxies form such intricate spiral patterns? The answer is not clear. One idea is that spiral arms are density waves, like traffic jams on a highway. Stars move through them, bunching up as they pass, creating the illusion of permanent arms. Another theory suggests that spirals may be shaped by interactions, galaxies tugging on one another with gravity, stirring stars into curved arms. Simulations can recreate spiral structures, but not with perfect consistency. Spirals are not rare. In fact, they are common, and yet their exact origin and stability remain unsettled. Why some galaxies form beautiful spirals while others become elliptical blobs is still an open question in astrophysics. When we look at the night sky and see the Milky Way stretched across it, we are looking from inside one of these mysteries. Our home galaxy's graceful arms are both familiar and unexplained. Fast radio bursts flash across the cosmos, and their cause remains a mystery. In 2007, astronomers detected a powerful radio signal lasting only a few milliseconds. Since then, hundreds more have been found scattered across the sky. These signals are called fast radio bursts, or FRBs. Each one releases as much energy as the sun does in a year, but in the blink of an eye. What causes them? Some FRBs repeat, suggesting they come from ongoing processes like magnetars, highly magnetic neutron stars that can flare with incredible energy. Others appear only once, hinting at catastrophic events such as the collapse of a star or the merger of compact objects. But no single explanation fits them all. FRBs travel across billions of light years, distorted and stretched by the matter between galaxies. They may even help us map the distribution of matter across the universe. But until we know their source, they remain cosmic puzzles. Every so often, the universe sends us a brief, powerful shout across the void. We can hear it. We can measure it. But we still do not know who or what is speaking. Pulsars shine with such perfect regularity that their precision still puzzles us. Pulsars are the collapsed remnants of massive stars, neutron stars that spin rapidly, sweeping beams of radiation across space like cosmic lighthouses. Discovered in 1967, they were so regular at first that scientists briefly wondered if they might be signals from intelligent life. Today, we know they are natural, but their precision remains astonishing. Some pulsars keep time better than our best atomic clocks, rotating hundreds of times per second without missing a beat. How can an object so extreme, a star crushed down to the size of a city, maintain such stability? The answer lies in their incredible density and strong magnetic fields, but the details are not fully understood. Pulsars can also glitch, suddenly changing their rotation speed in ways we cannot yet predict. These glitches may come from interactions deep within their superfluid cores, where physics is unlike anything on Earth. Pulsars are laboratories of extreme physics, but they still keep secrets. Their rhythms remain some of the most mysterious and precise signals in the universe. Magnetars erupt with strange bursts of energy we do not fully understand. A magnetar is a kind of neutron star with a magnetic field 1,000 times stronger than a normal neutron star and 1,000,000,000,000 times stronger than Earth's. These magnetic fields twist and snap, releasing sudden, violent bursts of radiation. Magnetars can release more energy in a single second than the sun produces in 100,000 years. We detect them as intense X-ray and gamma-ray flares. But what exactly sets off these eruptions remains uncertain. Are the bursts caused by starquakes, shifts in the crust of the neutron star under enormous magnetic stress, or are they triggered by sudden rearrangements of the magnetic field itself, releasing energy like a snapping cosmic rubber band? Some fast radio bursts have even been linked to magnetars, suggesting they may explain at least some of those mysterious signals. But the full picture is still missing. Magnetars are rare, with only a few dozen known, yet their power is staggering. They are reminders that the universe contains engines of energy we still struggle to understand. Cosmic rays strike Earth with incredible power, and we do not know exactly where they come from. Every second, high-energy particles called cosmic rays rain down on Earth from space. Most are protons traveling near the speed of light. Many come from the Sun or from supernovae. But some are so energetic, so powerful, that we have no clear idea where they originate. The most extreme cosmic rays carry the energy of a fast-pitched baseball packed into a single particle. No known process should be able to accelerate them to such enormous speeds. They may come from supermassive black holes, from active galaxies, or from exotic processes we do not yet understand. These particles crash into Earth's atmosphere, creating showers of secondary particles that we can detect on the ground. Observatories like the Pierre Auger Observatory in Argentina track them, trying to trace their paths back to their origins. But magnetic fields in space bend their trajectories, erasing the clues. Cosmic rays are constant visitors, yet their most powerful examples remain unexplained. They remind us that somewhere in the universe, nature runs particle accelerators far beyond anything humans can build. Vast cosmic voids stretch across space, and their origins remain uncertain. The universe is not evenly filled with matter. Instead, galaxies form a vast cosmic web, with clusters and filaments separated by enormous voids. Some of these voids span hundreds of millions of light-years and are nearly empty of galaxies. Why are they there? Simulations suggest that gravity pulls matter into filaments, naturally leaving empty regions behind. But the largest voids are bigger than expected, raising questions about how they formed. Do they hint at new physics, perhaps in the way dark energy shapes structure? Or are they simply statistical extremes, rare but possible? Voids affect how light travels across the universe. They may even offer clues about the nature of dark energy itself. But for now, their true origins remain uncertain. Looking into a cosmic void is like staring into nothingness on the largest possible scale. They are among the loneliest regions in existence, vast expanses with no clear explanation. How the universe will end is still an unanswered question. The universe had a beginning, but will it also have an end? Scientists consider several possibilities, each depending on the nature of dark energy and the balance of cosmic forces. In one scenario, the universe expands forever, cooling until stars burn out and galaxies fade, leaving only cold darkness. This is the heat death. In another, the expansion may eventually reverse, pulling everything back together in a big crunch. A third possibility is the Big Rip, where dark energy grows stronger over time, tearing apart galaxies, stars, planets, and eventually even atoms. Which will it be? We do not yet know. Observations suggest expansion will continue, but the details of dark energy remain too uncertain to decide. The universe may last for trillions of years, or it may meet a more dramatic fate. For now, the ultimate future of everything, of stars, galaxies, and life itself, remains one of the greatest unanswered questions in science. Something triggered cosmic inflation, but no one knows what. In the earliest fraction of a second after the Big Bang, the universe is thought to have expanded faster than the speed of light in a process called inflation. This theory explains why the cosmos appears so smooth and uniform, and why tiny fluctuations seeded the galaxies we see today. But what caused inflation? That remains a mystery. Some theories propose a field of energy, the inflaton, that briefly dominated the universe before fading away. Others suggest inflation is tied to the quantum structure of spacetime itself. We see its fingerprints in the cosmic microwave background, where patterns match what inflation predicts. But the true cause, and even whether inflation really happened as described, is still debated. Something made the universe grow unimaginably fast, creating the stage for everything that followed. But the spark that drove this inflation is still unknown, a hidden chapter in the story of creation. The origin of life on Earth is still unknown. Life on Earth began more than 3.5 billion years ago, but the details of its origin remain hidden. Fossil evidence shows that microorganisms were already thriving not long after the planet cooled. But how did non-living chemistry cross the threshold into life? One idea is that life began with simple molecules self-organizing into chains capable of storing information, perhaps RNA before DNA. Another is that life emerged from the energy-rich environment of hydrothermal vents on the ocean floor, where hot water, minerals, and chemistry combined. Still others propose that life's building blocks may have arrived from space, carried on comets or meteorites that bombarded the young Earth. Each idea has support, but none is proven. Scientists have managed to create amino acids and other basic molecules in laboratory conditions thought to mimic the early Earth, but producing a fully living system remains beyond reach. The origin of life may have been a unique event, or it may be a natural outcome whenever the right conditions exist. Until we uncover clearer evidence, the moment when chemistry first awakened into biology remains one of science's deepest mysteries. We do not know whether life began in the ocean or on land. Our planet offered many possible cradles for the first life. The ocean, covering much of Earth, seems like the obvious candidate. Hydrothermal vents, where hot water and minerals pour from the seafloor, provide rich chemistry and constant energy. Many scientists believe life may have begun there, with molecules assembling inside natural mineral compartments. But there is another possibility. Some researchers argue that shallow pools on land, subject to cycles of drying and refilling, could have concentrated molecules and driven the reactions needed to form life's building blocks. Ultraviolet light from the sun, often destructive, could also have powered key steps in these reactions. Both environments seem plausible. Each offers strengths and each faces challenges. The ocean dilutes molecules, making it harder for them to interact, while land-based pools may have been too unstable. Until stronger evidence emerges, we do not know whether life first stirred in the deep oceans or in the shallow waters of land. The answer remains hidden in the deep past, in rocks and fossils that have long since transformed. No one knows how the first living cells were formed. Life is defined not just by chemistry, but by organization. Modern cells are intricate structures with membranes that separate them from the outside world and molecular machines carrying out countless reactions. But how did the first cell arise from lifeless chemistry? One possibility is that fatty molecules naturally present on the early Earth formed bubbles that trapped useful chemistry inside. These primitive membranes could have allowed energy and molecules to flow while protecting fragile chains of RNA or proteins. Over time, the chemistry inside could have grown more complex, eventually becoming self-sustaining. Experiments show that simple membranes can indeed form spontaneously under the right conditions. But how the leap from these primitive compartments to the complexity of a living cell occurred is still unknown. This transition from disorderly chemistry to the first organized cell remains one of the great mysteries of biology. Until we understand it, we cannot say how life truly began. DNA chose a very specific shape, but why it did remains a mystery. All life on Earth uses the same molecule to store information: DNA. Its double helix is elegant and universal, carrying the instructions for every organism. But why this molecule, and why this shape? Chemistry allows for many possible ways to store information. RNA, for instance, is simpler and may have come first, but somewhere in life's early history, DNA took over as the master code. Its stability, its ability to replicate reliably, and its capacity to carry immense amounts of information made it uniquely suited. Yet we do not know why DNA's specific structure, a double helix with precisely paired bases, became the solution that all life depends on. Was it inevitable, dictated by chemistry? Or was it an accident, a single successful outcome among many failed alternatives? The universality of DNA suggests it may be the best answer nature could find. Still, why life chose this exact path remains an open question, hinting at deep mysteries in the chemistry that underpins existence. The origins of viruses are still unclear. Viruses are strange entities. They are not alive in the traditional sense. They cannot reproduce on their own, relying instead on hijacking the machinery of living cells. Yet they are not merely inert molecules. They evolve, adapt, and influence the course of life on Earth. Where did they come from? Some scientists think viruses are relics of the RNA world, survivors from before fully living cells evolved. Others believe they began as pieces of genetic material that escaped from cells and learned to copy themselves. A third possibility is that they were once living organisms that became stripped down to their simplest form. The reality may be that viruses originated through several different pathways, their beginnings as varied as life itself. What we do know is that they are extremely ancient. Some scientists even think viruses may have played an important role in the development of complex life by moving genes from one organism to another. Viruses sit in a strange place between living and non-living things, and their true beginnings remain one of biology's longest-standing mysteries. At some point in Earth's distant past, certain molecules crossed a boundary and became alive, while countless others did not. The reason for this difference is still unknown. Early Earth was a vast chemical laboratory. Simple molecules formed in many environments, from hydrothermal vents deep in the oceans to volcanic pools on land and atmospheres charged with lightning. Within this rich chemical environment, some molecules began linking together into more complicated structures, such as amino acids and nucleotides. Yet only a tiny portion of that chemical activity ever crossed the threshold into life. Why did those particular molecules succeed while others failed? What special qualities allowed some of them to organize themselves into systems capable of copying and sustaining themselves? Was life destined to appear once the proper ingredients were present? Or was it an extremely rare event that depended on a chain of unlikely accidents? Laboratory experiments show that many of the basic components of life can form naturally under the right conditions. However, building a fully self-sustaining and evolving system has proven far more difficult. The step from simple chemistry to true biology is enormous, and scientists still do not know exactly how that transition occurred. This uncertainty leads to even deeper questions. If life emerges naturally, wherever the right conditions exist, then the universe could be filled with living worlds. But if life arose through a rare accident, humanity may be incredibly alone in the cosmos. The mystery of why some molecules became alive while others remained inactive remains one of science's most profound unanswered questions. At present, we still do not know whether life exists anywhere beyond Earth. So far, Earth remains the only place where life is known to exist. Yet when we consider the scale of the universe, it seems improbable that life would arise in only one location. Our galaxy alone contains hundreds of billions of stars, and there are billions of galaxies spread across the cosmos. Despite this enormous scale, decades of searching have not produced clear proof of extraterrestrial life. Scientists have identified thousands of planets orbiting distant stars, many located within the so-called habitable zone where liquid water might exist. We also know that organic molecules are widespread in space. They have been detected in comets, within interstellar clouds, and on distant moons. Mars shows evidence that liquid water once flowed across its surface. Beneath the icy crusts of Jupiter's moon, Europa, and Saturn's moon, Enceladus, lie vast oceans. In other words, environments that could potentially support life appear to be common, and yet the universe remains silent. We have not detected signals from advanced civilizations. We have not found living microbes on Mars, nor have we discovered fossils of alien organisms. It is possible that life exists in many places, but is difficult for us to detect. On the other hand, life might be extremely rare, depending on conditions we do not yet understand. Until we discover even the simplest form of alien life, the question of whether life exists elsewhere will remain unanswered. Another possibility is that life beyond Earth might not resemble life here at all. Could living systems arise from a chemistry completely different from our own? At present, we simply do not know. All known life on Earth shares a common foundation built from carbon chemistry, liquid water, DNA, and proteins. But must life always follow that blueprint? Some scientists speculate that silicon, an element capable of forming long molecular chains and abundant throughout the universe, could potentially support alternative forms of life. Others imagine organisms that might use ammonia instead of water as a solvent. Some theories even propose exotic forms of life thriving in the methane lakes found on Saturn's moon Titan. Still others speculate about even stranger possibilities: systems based on plasma, magnetic fields, or patterns of information that behave like living processes. The truth is that our current definitions of life are shaped entirely by one example: Earth. It may turn out that carbon and water are the only practical ingredients for life. But it is also possible that the universe contains living systems far stranger than anything we can currently imagine. If we eventually discover alien life, it may look nothing like us and may challenge our understanding of what it means to be alive. Another major question concerns how common truly habitable worlds are. Astronomers have already discovered thousands of planets orbiting distant stars. Many of these worlds are rocky planets similar in size to Earth, and some orbit within regions where temperatures might allow liquid water to exist. But the real question is how many of these planets are actually habitable. Habitability involves much more than simply being the right distance from a star. A planet must also possess a stable atmosphere, protection from harmful radiation, and long-term environmental stability. Some planets may be scorched by intense radiation from their stars. Others may be frozen because they receive too little heat. Even moons might host life beneath thick layers of ice covering hidden oceans. However, measuring these details across vast interstellar distances is extremely difficult. The Milky Way may be filled with habitable worlds, or they may be rare gems scattered among billions of planets. For now, scientists cannot say. Each new discovery brings us closer to an answer, But the true frequency of Earth-like environments remains one of astronomy's greatest mysteries. Ultimately, this leads to the oldest question humanity has ever asked. Are we alone? For as long as humans have gazed up at the night sky, we have wondered whether life exists beyond our planet. Even with the immense size of the universe and the countless planets that orbit distant stars, we still have no definitive answer. Scientists listen for signals using powerful radio telescopes. Space probes explore nearby planets and moons. Telescopes analyze the atmospheres of distant worlds, searching for chemical signs that could indicate life. But so far, we have found only silence. It could be that life itself is common, but intelligent civilizations are extremely rare or short-lived. It could also be that life at every level is extraordinarily rare, and that humanity represents a unique accident in cosmic history. Another possibility is that life exists everywhere, but remains hidden from us by vast distances or unfamiliar forms. For now, the question remains unresolved. Are we a single spark of life in an empty universe? Or just one voice among countless others in a cosmic chorus we have not yet heard? Until evidence appears, the answer to this ancient question remains unknown. Another deep mystery concerns consciousness itself. Every thought you experience, every memory you hold, and every moment of awareness appears to arise from activity within the brain. Scientists can measure electrical signals traveling across networks of neurons. They can turn consciousness off using anesthesia and observe how brain activity changes when you focus on a picture, sound, or idea. Yet none of these observations explain why consciousness exists at all. Why should patterns of electrical activity in neurons produce the feeling of being alive and aware? Brain scans can show activity in the visual cortex when someone looks at a sunset, but they cannot explain why that experience comes with the vivid sensation of red and gold colors inside the mind. Similarly, scientists can identify circuits that process sound, but that does not explain why hearing a favorite song can feel deeply emotional. Researchers have proposed several ideas. Some believe consciousness emerges when information flows widely across the brain. Others think it appears when neurons form specific patterns of activity. Some theories even suggest that consciousness may be a fundamental feature of the universe itself. But none of these theories fully explains how matter becomes mind. Consciousness is the most familiar experience we have. It is what you're experiencing right now. Yet when we attempt to explain it scientifically, it remains one of the deepest mysteries in existence. Closely related to consciousness is the strange phenomenon of dreams. Every night while we sleep, our minds create entire worlds. Sometimes these dreams are vivid and realistic, filled with familiar people and places. Other times they are strange, fragmented scenes that disappear moments after we wake. Despite being a universal human experience, the true purpose of dreams is still unclear. Some scientists believe dreams help the brain rehearse situations or reinforce important memories. Others think dreaming helps regulate emotions, allowing the mind to process fear, sadness, or conflict in a safe mental environment. Another theory suggests dreams are simply the result of random neural activity during sleep, with the brain attempting to assemble these signals into stories. What makes dreams particularly puzzling is how powerful they can feel. A nightmare can cause real fear even though you are safe in bed. A pleasant dream can leave you in a good mood for hours after waking. In some cases, dreams even appear to help solve problems. Writers, artists, and scientists have described creative breakthroughs that arrived while they were asleep. Researchers know that the brain remains very active during dreaming, especially during REM sleep, when the eyes move rapidly beneath closed eyelids. However, the deeper purpose of dreams remains unclear. Dreams are familiar nightly journeys into strange landscapes, yet their true meaning remains hidden. Another curious mystery involves how we experience time. There are moments when time seems to slow dramatically. A sudden accident, a moment of fear, or an intense experience. Yet there are also times when hours seem to pass in an instant, such as during a holiday, or when we are deeply engaged in something we enjoy. The ticking of a clock remains constant, but our perception of time can vary dramatically. Why does this happen? Scientists are not certain. One possibility is that the brain contains an internal timing system influenced by emotions. Strong emotions such as fear might accelerate this internal clock, making moments feel longer, while calm states may slow it down. Another theory suggests that the brain measures time based on the number of events it processes. Moments filled with new experiences may seem longer, while routine activities pass quickly. This idea might explain why childhood summers often felt endless, while adult years seem to pass more quickly. New experiences stretch our perception of time, while familiar routines compress it. However, these explanations remain incomplete. What we do know is that our mental experience of time is flexible. It can stretch, shrink, or even seem to pause entirely. The seconds and minutes remain constant, but our perception of them follows rules we do not yet fully understand. Memory is another area filled with unanswered questions. Every moment of your life, your first day of school, joyful memories, painful regrets, is stored somewhere inside your brain. Yet the exact way these memories are stored and later recalled remains only partly understood. Scientists know that memories are not stored like files in a cabinet. Instead, they exist as patterns of activity distributed across networks of neurons in different regions of the brain. The hippocampus plays a key role in organizing these patterns, acting somewhat like an index that helps locate memories when needed. But exactly how a memory is encoded and later retrieved is still not fully clear. Interestingly, memories are not perfectly stable. When we recall a memory, it can be modified before being stored again. In some cases, people even develop false memories that feel completely real. Why do certain memories remain vivid for decades, while others fade within days? Why can a simple smell suddenly bring back a detailed scene from childhood? Experiments have revealed glimpses of how memory works. Scientists have identified neurons that activate when a particular face appears and have observed brain activity patterns associated with recalling past experiences. But the complete mechanism remains elusive. Memory is the thread that connects our past to our present identity. It shapes who we are and how we understand the world. Yet the underlying machinery, how experiences become part of us, and how they return years later, remains one of neuroscience's great mysteries. Our emotions run deep within us, yet their true origins remain mysterious as well. Emotions shape nearly every part of human life. Joy moves us ahead. Fear makes us hesitate. Anger can ignite in a moment. Sadness can press down like a weight. But where do these feelings actually come from? Scientists understand that emotions involve both the brain and the body. Your heart pounds when you're frightened. Your stomach tightens when anxiety rises. Tears gather when sorrow comes. Yet the true source of these feelings is still debated. Are emotions ancient survival mechanisms built into our biology, or are they assembled by the brain and shaped by memory, culture, and personal interpretation? We know some brain regions are involved. The amygdala is linked to fear, the insula to disgust, and the prefrontal cortex to emotional control, yet there is no single center where emotions simply live. Music can send chills across your skin. A scent can awaken powerful nostalgia without warning. Sometimes we cannot even explain why we feel what we feel. Emotions are powerful guides. They direct our decisions, often more strongly than logic does. Yet the way they arise and the way they grip both body and mind remains one of the most personal mysteries of being human. Creativity arrives in sudden flashes, but its source remains hidden. An artist faces a blank canvas. A writer stares at an empty page. A scientist wrestles with a problem that refuses to yield. Long stretches may pass with nothing at all. Then, without warning, an idea appears. It comes alive all at once, clear, unexpected, and full of energy. But where did it come from? Creativity feels like a spark, yet its origin remains concealed. Some believe creativity is the brain combining old ideas into new forms. Others think it depends on stepping back and letting the subconscious continue working while the conscious mind relaxes. Many famous breakthroughs did not come at desks. They came in dreams, under a shower, or during a quiet walk. Brain scans suggest different systems are involved, with some generating possibilities and others evaluating them. But even that does not explain the actual moment of inspiration. Why does an answer appear so suddenly and with such power? Why do some people seem filled with ideas while others struggle to find them? Creativity is one of humanity's greatest powers. It shapes art, science, invention, and progress. Yet the place ideas come from, that silent jump from nothing into something, remains a mystery we still cannot fully explain. Déjà vu makes the present feel repeated, and no one fully knows why. You walk into a place you have never visited, and suddenly the entire scene feels oddly familiar. You feel as though you already know what happens next, even though you do not. This is déjà vu, one of the strangest experiences of the mind. Scientists think it may be caused by a glitch in memory. Perhaps the brain sends a false signal of familiarity without any real memory behind it. Others suggest that one part of the brain processes an experience a fraction of a second before another part does, making the moment feel as though it is happening again. Still others think the sensation comes from hidden similarities between the present scene and some forgotten past experience, tricking the brain into feeling recognition. What makes déjà vu so puzzling is its force. For a brief moment, reality feels doubled, both new and remembered at once. Almost everyone experiences it, yet no one can predict exactly when it will happen or why. Déjà vu reminds us that memory and perception are fragile, and that the brain can deceive us in ways we still do not understand. Placebos can produce healing, but the force behind them is still mysterious. Imagine swallowing a pill, being told it will reduce your pain, and then genuinely feeling relief, even though the pill contained no active medicine. This is the placebo effect, and it is real. Doctors have seen placebos reduce pain, ease depression, and even soften symptoms of Parkinson's disease. The effect is often linked to expectation. The belief that a treatment will help can trigger real changes in both brain and body. Placebos can release the body's natural painkillers, shift brain chemistry, and even influence the immune system. What makes the placebo effect so remarkable is that it can sometimes work even when people know they are taking one. Somehow, the ritual of treatment, the pill, the doctor, the expectation, activates hidden pathways of healing. Yet why some people respond strongly to placebos while others barely respond at all remains unknown. The placebo effect blurs the line between mind and body, showing that belief itself can sometimes heal in ways we still do not fully understand. We do not even fully know why sleep is necessary. Every night, we surrender to it. We close our eyes, drift into dreams, and lose waking awareness for hours. But why do we need sleep in the first place? If you think about it, sleep seems risky. In the wild, a sleeping animal is vulnerable. And yet every species sleeps in some form. That suggests sleep is essential. But essential for what? Some scientists believe sleep helps the brain store memories and strengthen learning. Others think it clears away waste products, cleaning harmful buildup from the brain. Sleep may restore energy, regulate emotions, and support the immune system. It may also help the brain reset and rebalance its connections. And still, no single explanation accounts for all the evidence. Different animals sleep in very different ways. Dolphins can sleep with only one half of the brain at a time. Some birds rest while flying. Some species need very little sleep at all. What we do know is that without sleep, both mind and body begin to fail quickly. Why we spend about a third of our lives in this state remains one of science's great unanswered questions. We still do not fully understand why aging happens the way it does. Every living creature on Earth grows old. Skin wrinkles, hair turns gray, muscles weaken. Eventually, the body begins to break down. But science still cannot completely explain why aging occurs or why it happens so differently across species. One explanation points to DNA. Each time a cell divides, the protective caps at the ends of chromosomes, called telomeres, become shorter. Eventually, the cell can no longer divide. Another explanation blames gradual damage. Oxygen molecules and other chemical byproducts slowly wear down cells over time, leaving behind accumulating harm. Others see aging as a trade-off shaped by evolution. Energy is directed toward growth and reproduction early in life, but later the body becomes more vulnerable to decline. Yet nature also offers exceptions. Some turtles and fish show little sign of aging. Certain jellyfish can return to earlier stages of life, seeming to escape decline altogether. Naked mole rats live far longer than expected and show unusual resistance to many diseases associated with age. Why do some creatures resist aging while humans are overtaken by it? And why does aging in us follow such a steady and familiar pattern? The answers remain unclear. Solving this mystery could transform medicine. But for now, aging remains a riddle written deep within our cells. The true limits of human lifespan are still uncertain. The longest confirmed human life reached 122 years. But was that the real ceiling of human biology, or simply an extraordinary exception? No one knows for sure. Some researchers argue that humans do have a hard biological limit. Beyond a certain point, the body can no longer repair itself fast enough to keep going. Data suggests survival rates fall sharply after age 110, hinting at a possible cap. Others argue there may be no fixed maximum at all, only increasing chances of disease, weakness, and death. What makes this especially puzzling is that average life expectancy has risen dramatically because of medicine, sanitation, and better nutrition, yet the maximum human lifespan has changed very little. Almost no one lives beyond 115, no matter the era or the country. Still, scientists continue searching for ways to extend life. They study families of superagers who stay healthy deep into old age. They search for genes that resist disease and test drugs that slow aging in animals. Could humans one day live to 150 or even 200? The evidence offers possibilities, but not certainty. The upper boundary of human life remains hidden, waiting for discovery, if indeed it can be pushed further at all. Some animals can regrow entire body parts, and we still do not fully understand how. If a salamander loses a leg, it can grow another. If a starfish loses an arm, it rebuilds it slowly. Some worms can regenerate an entire body from only a fragment. In nature, regeneration is surprisingly common. Humans, by contrast, can do it only in very limited ways. A child may regrow part of a fingertip, but a lost limb does not come back. So why can they do it and we cannot? Scientists studying salamanders have found that when injury occurs, cells near the wound appear to reset themselves, returning to a flexible state similar to that of embryonic cells. From there, they can grow into muscle, bone, and nerve in the right arrangement. Humans possess many of the same genes, yet for reasons still unclear, our bodies do not activate them in the same way. If we could unlock this ability, medicine would be transformed. Damaged hearts might repair themselves. Spinal cords could regrow. Lost limbs might return. And yet, even after decades of research, the full blueprint of regeneration remains hidden. Why nature gave this power to some creatures while withholding it from us is still a mystery. For now, regeneration belongs to salamanders, starfish, and a handful of other organisms, a wonder we can only watch in amazement. Some creatures live far longer than expected, and we still do not fully know why. Most animals seem to follow a rough pattern. Small bodies tend to have shorter lives, while larger ones often live longer. Mice live only a few years. Elephants live for decades. Humans, with our long lives, already stand out among primates. Yet nature contains remarkable exceptions that seem to ignore these rules entirely. The Greenland shark moves beneath Arctic waters for centuries with a lifespan that may exceed 400 years. Bowhead whales live in icy seas for more than 2 centuries. Tiny naked mole rats survive around 10 times longer than similar rodents and show striking resistance to age-related decline. Some clams have even been found alive after more than 500 years. Why? Scientists have found clues, but not a full answer. Proteins that seem unusually resistant to damage. DNA repair systems that appear to work with greater efficiency. Metabolisms that run at an astonishingly slow rate. Yet no single explanation accounts for all of them. Each species seems to possess its own secret to long life, and humans still cannot reproduce it. These animals remind us that aging is not some unchangeable law of nature, but a mystery with many possible answers. If we could uncover their biological secrets, we might one day discover new ways to lengthen our own lives. For now, they remain enduring mysteries of the natural world. Some animals can survive being frozen solid, yet we still do not fully understand how. Imagine being locked in ice. Your blood crystallized, your heart stopped, your body stiff and motionless. For most living things, that would mean death, but not for all creatures. The wood frog of North America freezes during winter. Its heart stops beating. Its body becomes rigid. Yet when spring warmth returns, the frog thaws and hops away as if nothing happened. Certain insects and fish can survive similar conditions, and tardigrades, the tiny creatures known as water bears, can endure conditions far beyond freezing, even surviving the vacuum of space. How do they manage it? Some species flood their bodies with antifreeze-like molecules that stop ice crystals from tearing their cells apart. Others rely on sugars that stabilize tissues during freezing. But the exact way their brains, hearts, and other fragile organs survive months of inactivity is still not fully clear. If we could learn this trick, it could transform organ transplants, medicine, and perhaps even space travel. We might preserve organs for months or place humans into hibernation for long journeys. But for now, That secret belongs only to these resilient survivors, creatures that seem almost to mock the usual rules of life and death. Whales can live for centuries with surprisingly little cancer, and scientists do not fully know why. The bowhead whale can survive for more than 200 years, moving through the icy waters of the Arctic. What makes this so remarkable is not only its age, but also its health. Despite its enormous body, filled with billions of cells and exposed to centuries of possible mutations, cancer remains unusually rare. This is part of what scientists call Peto's paradox. In theory, bigger animals with more cells should face higher rates of cancer. But whales, elephants, and other giants do not. Somehow, they resist it. In elephants, researchers have discovered extra copies of tumor suppressor genes, like additional biological defenses. In whales, the explanation is less clear. Maybe their DNA repair systems are exceptionally strong. Maybe their slow metabolism limits damage over time. Or maybe they possess entirely unique biological pathways that we have not yet uncovered. If we could solve this mystery, it might transform cancer treatment in humans. Whales seem to have solved part of the puzzle of long life without disease. But for now, their secret remains beneath the ocean, still unsolved. Birds can sense Earth's magnetic field, but the exact mechanism remains uncertain. Every year, birds migrate across entire continents. Tiny warblers fly from Europe to Africa. Arctic terns cross oceans and circle the globe. They travel thousands of miles with astonishing precision. Part of their ability appears tied to Earth's magnetic field, but how they detect it remains unclear. Some evidence points to microscopic crystals of magnetite in their bodies, acting like internal compasses. Other studies suggest certain proteins in their eyes may allow them to perceive magnetic fields as faint visual patterns. But no single theory explains everything. What we do know is that their navigation is incredibly exact. Even on cloudy days, when the sun and stars are hidden, birds stay on course. Even when released in unfamiliar places, they often still find their way. It is a sense humans do not possess, as though birds can detect an invisible layer of reality closed off to us. For them, the world seems to carry direction woven into its very structure, a compass we still do not fully understand. Monarch butterflies cross continents guided by a map we cannot read. Every autumn, delicate monarch butterflies begin an extraordinary journey. They travel thousands of miles from the northern United States and Canada to a few mountain forests in central Mexico. There, they gather in thick clusters, covering trees in shimmering orange. What makes this migration even more astonishing is that no single butterfly completes the entire round trip. The butterflies returning north in spring are several generations removed from those that left in the fall. Yet somehow they still reach the very same groves year after year. Scientists know monarchs use the sun as a compass, adjusting their direction according to the time of day. They may also detect Earth's magnetic field. But how this navigational knowledge is passed across generations, how a butterfly that has never made the journey somehow knows exactly where to go, remains a mystery. It is one of the most breathtaking migrations on Earth, guided by a hidden map no human has ever seen. Migrating animals cross immense distances, yet we still do not fully know how they guide themselves. The natural world is filled with epic migrations. Salmon are born in mountain streams, swim out to the sea, and years later return to the very same stream to reproduce. Sea turtles emerge from the ocean and crawl onto the exact beach where they once hatched. Birds, whales, and insects cross the planet with astonishing precision. Scientists have uncovered hints. Some animals may navigate by the stars, the sun, or the tilt of Earth's axis. Others may rely on magnetic fields or subtle sensory cues beyond our understanding. Yet none of these explanations fully accounts for their extraordinary precision. How does a bird return to the same tree each year? How does a turtle cross an entire ocean to find one patch of sand? These journeys remain only partly explained, guided by senses we do not yet fully understand. Migration is one of life's oldest patterns, a vast and mysterious rhythm written into animal instinct. Homing pigeons can return home from almost anywhere, and the mystery remains. For centuries, people have marveled at homing pigeons. Release one hundreds of miles away, and it will rise into the air, circle briefly, and then head straight back to its loft. No map, no guide, just an unseen sense of direction. Researchers have proposed many explanations. Some think pigeons use the sun as a compass, adjusting their path according to time. Others suggest they can detect Earth's magnetic field, like a built-in navigation system. Still others point to smell, proposing that pigeons create a scent map of their home region and follow it back. But none of these ideas fully explains their uncanny accuracy. Even when released in unfamiliar places beneath cloudy skies, pigeons still manage to find their way home. Some hidden compass in their biology continues to guide them. For pigeons, the world appears full of invisible signals directing them across the sky. For us, it remains an unsolved puzzle. No one knows exactly how humans first developed language. Language is one of the defining features of humanity. Through it, we share ideas, preserve stories, and build civilizations. But its beginning remains one of the greatest mysteries in human history. Our closest relatives, chimpanzees and bonobos, communicate with sounds and gestures, yet none approach the complexity of human speech. At some point, our ancestors crossed a boundary, moving from simple calls into structured language, complete with grammar, abstraction, and endless expressive power. But when did that happen? And how? Some theories suggest language began with gestures, and spoken words came later. Others propose that rhythm, chant, and song slowly evolved into speech. Archaeology gives us clues in the form of carvings and symbolic art tens of thousands of years old, suggesting the people who made them already possessed complex communication. But the actual sounds they spoke left no trace behind. Language allows us to describe what is absent, to plan ahead, to imagine, and to dream. It is both a survival tool and a window into thought itself. Yet the first spark of language, the moment when humans first truly spoke, has vanished into deep time. We can only imagine the conversations that started it all. Laughter is universal, yet its origins remain mysterious. Everywhere on Earth, people laugh. The sound crosses culture, age, and language. Babies laugh long before they can speak. Groups laugh together, and the feeling spreads easily from one person to another. Yet why we laugh and how laughter first evolved is still uncertain. Some scientists think laughter began as a signal of safety. Early humans may have laughed to show that danger had passed, turning tension into relief. Others trace it back to playful primates, whose panting sounds during wrestling and chasing resemble the rhythm of human laughter. But laughter is more than a survival signal. It lowers stress, strengthens social bonds, and releases powerful chemicals that calm the body. Strangely, we laugh not just at jokes, but also out of relief, embarrassment, and sometimes even sadness. At times, laughter bursts out when it seems to make no sense at all. Why should a breathy burst of sound carry such force? We still do not know. What we do know is that laughter is ancient, universal, and deeply mysterious. It is the shared music of joy across humanity, with roots still hidden in our past. Music moves us in profound ways, yet science still cannot fully explain why. A melody can bring tears to our eyes. A rhythm can make the heart pound faster. A song can reconnect us to memories we believed were long gone. Music seems to have no obvious survival purpose, yet it shapes human life in every culture on Earth. Why? We still do not know. Some researchers think music evolved as a kind of social glue, helping early communities bond through rhythm, dance, and song. Others suggest it began as part of courtship, a way of displaying health, energy, and skill. Still others argue that music is a byproduct of language and memory, a beautiful accident produced by evolution. What makes music even more mysterious is its power. Stroke patients who struggle to speak may still be able to sing. People with dementia can remember song lyrics long after much else has disappeared. Music can synchronize heartbeats in groups, soothe newborn babies, and stir entire armies to move. Why should organized sound reach so deeply into both mind and body? Science still has no clear answer. Music remains one of the most universal and mysterious forces in human life, an invisible thread that binds us together. Love is powerful and complex, yet its full nature remains beyond complete explanation. Love shapes human life more than almost anything else. It joins parents to children, partners to each other, and friends across years and distance. It inspires art, sacrifice, and joy. Yet science still cannot fully define what love is. Biology reveals part of the picture. Love floods the brain with chemicals such as dopamine and oxytocin, which are linked to reward and bonding. Evolutionary theory suggests love developed in part to keep parents together long enough to care for vulnerable children. But those explanations do not capture the whole experience. Why does love sometimes arrive suddenly and overwhelm us? Why does it last for a lifetime in some people and fade in others? Why do people risk everything for it, even when reason says otherwise? Love is not just chemistry or instinct. It is memory, story, imagination, and something beyond all of them. We can trace some of its effects in the brain, but not its meaning. Love is both universal and impersonal, something shared across humanity, yet experienced differently by every individual. Its full nature remains one of the deepest mysteries of being alive. Humans cry emotional tears, and no one fully knows why. Tears protect the eyes, washing away dust and salt. But humans alone seem to cry for reasons beyond simple biology, when we are sad, joyful, frustrated, or overcome with laughter. Why? One idea is that tears serve as a social signal, showing vulnerability and drawing compassion from others. Another suggests they may help release stress-related chemicals, though the evidence is mixed. Tears may also strengthen human bonds by making inner feelings visible to those around us. What deepens the mystery is that we cry for opposite reasons. Tears come with grief and with joy, with heartbreak and with relief. They can fall quietly in solitude or burst out in the middle of laughter. No single theory fully explains all of this. Tears remind us that we are not only logical beings, but emotional ones as well. They make the invisible visible, carrying feelings from the inside into the outside world. But why humans alone evolved this response remains unsolved, a secret hidden in every tear that falls. Myths appear in similar forms across cultures, and we still do not fully understand why. From deserts to islands, mountains to forests, people separated by oceans have told stories that echo one another. Myths of great floods, sky gods, tricksters, and underworlds appear again and again. Why does this happen? Some think the human mind is naturally shaped for storytelling, and that certain themes arise again and again from shared human experience: the fear of death, the hope of renewal, the awe inspired by the heavens. Others believe ancient myths spread through migration and trade, leaving traces in distant lands. Still others wonder whether myths emerge from deeper patterns in the human brain, symbols drawn from the same inner landscape. Whatever the explanation, myths carry truths that cultures consider important. They explain what seems unexplainable, bind communities together, and pass wisdom from one generation to the next. Yet the repeated appearance of similar stories across the world, even where contact seems unlikely, remains a mystery. Humans often cooperate with strangers, and the roots of this instinct are unclear. Compared with most animals, humans are unusual. We do not only help family or close allies, we also help strangers. We donate blood. We build communities. We take risks for people we may never meet. Why? Evolutionary theories suggest cooperation gave groups an advantage, helping them survive against rivals. Others point to reciprocal altruism, the idea that help offered today may be returned in the future. But humans often go beyond calculation. We volunteer, share, and sacrifice, even when no reward is expected. Experiments show that even very young children often choose to help before they fully understand rules, duty, or social expectations. Something in us seems naturally drawn toward cooperation. But where did it come from? Did it grow out of survival alone, or from something deeper? A moral instinct written into the human mind. The desire to help strangers remains one of humanity's most beautiful and mysterious traits. Civilizations rise and fall, but the deepest forces behind that pattern remain debated. Throughout history, powerful civilizations have grown, flourished, and then collapsed. The Maya, the Indus Valley Civilization, Mesopotamia, Rome, all rose to greatness and then fell. But why does civilization so often follow this arc? Some point to climate change, drought, and natural disaster. Others blame war, corruption, or the depletion of resources. Still others believe civilizations contain within themselves repeating patterns of growth and decline, cycles that appear again and again across different eras and places. The truth may involve all of these factors, or something else entirely. What is striking is how suddenly collapse can happen. Great cities are abandoned. Knowledge is lost. Entire generations disappear into silence. Civilization itself is fragile, and the forces that cause it to thrive or fail are not fully understood. We live inside vast and complex societies, yet history reminds us that nothing lasts forever, and the reasons why remain partly mysterious. Human curiosity drives us, but its source remains uncertain. Why do we wonder? Why do we look at the stars and ask questions no other creature seems to ask? Curiosity is one of humanity's defining traits, yet where it comes from is still not fully clear. Some say curiosity began as an extension of survival, helping us search for food, shelter, and safety. Others believe it became an evolutionary advantage, pushing us to explore, invent, and imagine. But curiosity often goes far beyond survival. It drives us to study galaxies billions of light years away, to decipher ancient languages, and to ask questions with no immediate practical use at all. Children show curiosity almost from the start, reaching toward the unknown and asking endless questions. It seems deeply built into us. But why this hunger for knowledge exists, why this restless drive to understand, still has no final explanation. Curiosity pushes humanity forward, shaping science, art, and exploration. Yet its source, the spark behind the question why, remains one of life's mysteries. Storytelling is universal, but no one fully knows why we need it. Every culture tells stories, around fires, on stages, in books, and in films. Humans shape words into narratives. Stories carry heroes and villains, struggle and triumph. They entertain, they teach, they inspire. But why are they universal? Some suggest storytelling helps pass on knowledge, packaging lessons in memorable form. Others think it binds communities together by giving people shared myths and values. Some see it as a kind of practice, letting us rehearse challenges and decisions safely in imagination. But stories often go beyond those purposes. They create worlds that never existed, make us feel deeply for people who are not real, and remain in our minds for years. No other species seems to do this. Why do humans need stories? Why do we return to them again and again? We do not know. What we do know is that storytelling is as ancient as language itself, a thread running through every culture and connecting us all. Lightning sometimes appears as glowing balls of fire, and we still do not know exactly how. Most people think of lightning as a sudden flash in the sky, a jagged bolt followed by thunder. But there is a far stranger phenomenon that has puzzled observers for centuries: ball lightning. Instead of a brief strike, it appears as a glowing sphere of light, drifting silently across fields or even inside houses. Witnesses describe orbs about the size of a grapefruit, shining orange, white, or blue, sometimes lasting for several seconds before vanishing or exploding with a pop. For a long time, ball lightning was dismissed as myth or illusion. But in recent years, credible reports and even a few scientific recordings have suggested that it is real. The problem is that no one knows exactly what it is. Some theories describe plasma trapped by electromagnetic fields. Others suggest glowing silicon vapor produced after a lightning strike. Some point to chemical reactions ignited in the air, but no explanation fits every report. The mystery grows deeper because ball lightning has sometimes been seen indoors, even appearing to pass through windows without breaking them. It seems to challenge ordinary physics, behaving at times like matter and at times like light. Despite thousands of reports, it remains rare, unpredictable, and unexplained. Ball lightning drifts through history as one of nature's strangest and most beautiful mysteries, a ghostly fire in the sky. Earthquake lights appear in the sky, and no one fully knows what causes them. During some major earthquakes, witnesses report strange lights in the air. They appear in many forms: flickering blue flames along the ground, lightning-like flashes over cities, or glowing orbs hovering near fault lines. These earthquake lights have been described for centuries, and modern cameras have captured them as well, confirming that they are real. What causes them remains uncertain. One theory suggests that rocks under great stress release electrical charges during an earthquake, producing light in the air. Another idea is that tectonic forces ionize gases near the ground, causing them to glow. But not every earthquake produces lights, and the appearances vary widely. In some cases, the lights even appear before the earthquake itself, leading some to wonder whether they might serve as a warning sign. But because they are so rare and so unpredictable, they are extremely hard to study. Earthquake lights remain among the strangest natural mysteries on Earth. Brief flashes of eerie glow appearing in the middle of disaster, reminders that the planet may still hide secrets written in rock and fire. Some volcanoes erupt with overwhelming violence, and the exact triggers are still not fully understood. Volcanoes are among the most destructive forces on Earth. Most eruptions are dramatic but relatively contained. lava flows, rising ash clouds, and moderate explosions. But every so often, a volcano erupts with unimaginable power, hurling enough material into the atmosphere to change climate patterns and spread destruction across entire continents. What causes some eruptions to become so catastrophic? Scientists know that pressure builds as magma rises and gases expand, yet the precise tipping point remains uncertain. Some volcanoes sit quiet for centuries and then erupt with little warning. Others smoke, rumble, and tremble for years without exploding at all. The real mystery lies in what shifts the balance from silence into disaster. Events like Krakatoa in 1883, Tambora in 1815, and the eruption of Mount Toba about 74,000 years ago released energy on a scale comparable to nuclear weapons. Toba may even have brought humanity close to extinction. Yet modern science still cannot say with confidence which volcanoes will erupt this way, or exactly when. We track tremors, measure gas emissions, and scan magma chambers, but the internal mechanics of super eruptions remain hidden. Volcanoes remind us that Earth itself is active, powerful, and still full of mysteries we do not yet control. Why plate tectonics began on Earth is still debated. The surface of our planet is alive with motion. Continents drift, mountains rise, oceans open and close. All of it is driven by the slow movement of tectonic plates. Without plate tectonics, Earth would not have its landscapes, its earthquakes, or its volcanoes. Life itself may even depend on this constant churning. But why did this process begin here and not on other planets? Mars and Venus do not show active plate tectonics. Their crusts are mostly stagnant, locked in place. Somehow, billions of years ago, Earth's outer shell fractured into vast plates that continue to slide and grind against one another. Did water act like a lubricant, weakening rock and making movement possible? Did Earth's internal heat settle into just the right balance between rigidity and flow? Or did ancient impacts crack the crust and start the process? We still do not know. Computer models offer competing possibilities, but none fully explains why Earth alone developed this system. Without plate tectonics, the carbon cycle that helps regulate climate might break down, leaving the planet barren. Plate tectonics helps make Earth dynamic and habitable. Yet the reason it started here, and why it appears unique in our solar system, remains an unsolved mystery. The origin of Earth's water is still uncertain. Water covers most of our world, filling oceans, rivers, lakes, and clouds. It is essential for life. And yet its ultimate source remains one of science's great puzzles. Did water arrive on asteroids and comets during the violent early history of the solar system? Some evidence supports this idea, since many space rocks contain ice. But the chemical signature of Earth's water does not always match the water found in comets. Another possibility is that water was present from the beginning, locked deep within Earth's mantle, and slowly released to the surface over immense stretches of time. Perhaps both ideas are true. Some water may have formed with Earth, while some was delivered from space. But the balance between those two sources is still debated. What we do know is that Earth is unusual. Neighboring planets such as Venus and Mars are now dry, their water either lost to space or trapped away. Something about Earth allowed oceans to collect and remain stable. Water feels so ordinary that we forget how strange it really is. Every drop you drink carries the mystery of its origin, a riddle reaching back to the birth of our planet. The far side of the moon looks strangely different, and we do not fully know why. For thousands of years, humanity saw only one face of the moon. The far side remained hidden until spacecraft revealed it in the 20th century. What they showed us was surprising. The near side, the face familiar to us, is covered in dark maria, wide plains of ancient cooled lava. The far side looks very different. It is rugged, heavily cratered, and mountainous, with almost no maria at all. Why should the two sides of the same moon be so different? One idea suggests the moon once experienced uneven heating, with Earth's gravity warming one side more than the other. Another proposes that an ancient collision reshaped one hemisphere but left the other mostly unchanged. Some theories point to internal differences, such as crust thickness or ancient volcanic activity, but no explanation fits perfectly. The moon should seem more symmetrical than it does. Instead, its hidden face carries marks and mysteries that resist simple answers. Even now, as orbiters circle it and landers touch down, the far side of the moon keeps much of its secret, as though half of it still remains a stranger to us. Earth's core generates a magnetic field, but the details remain uncertain. Deep below our feet, more than 3,000 kilometers down, lies Earth's core, a vast region of molten iron and nickel surrounding a solid inner center. The motion of this metal generates Earth's magnetic field, protecting us from solar wind and cosmic radiation. Without that shield, our atmosphere might have been stripped away, leaving Earth barren like Mars. Yet despite its importance, we still do not fully understand how this system works. We cannot drill down to the core, so we depend on indirect evidence, seismic waves, magnetic records, and computer simulations. We know the outer core flows like a liquid, and that this motion drives the geodynamo. But why Earth's magnetic field sometimes weakens, shifts, or fully reverses remains unclear. Other planets make the mystery deeper. Mars once had a magnetic field, but lost it. Why did Earth keep its protective shield while Mars did not? The beating heart of our planet remains hidden from direct study. We see its effects in compasses, auroras, and even in the survival of life itself. But its inner workings are still mysterious. Earth's magnetic poles sometimes reverse, and the reason is still unknown. From time to time in Earth's history, the magnetic poles swap places. North becomes south, and south becomes north. Ancient rocks record these reversals, preserving a flip-flop pattern that stretches back millions of years. The last complete reversal happened around 780,000 years ago. But why do these flips occur? Scientists think turbulence in the liquid outer core, the engine of Earth's magnetic field, sometimes becomes unstable, causing the field to weaken and then rebuild in the opposite direction. But the exact trigger remains uncertain. Sometimes reversals happen relatively quickly. Sometimes they unfold over thousands of years. And sometimes the field only weakens without fully flipping at all. The mystery becomes even more serious when we consider the effects. During a reversal, the magnetic field weakens, exposing Earth to greater amounts of radiation from space. Would that disturb ecosystems? Did past reversals influence evolution? We do not know. What we do know is that Earth's magnetic field is not permanent. One day, north will again become south, and the reason remains hidden deep inside the planet. Ice ages come and go, and we still do not fully know what drives them. For millions of years, Earth's climate has swung between long cold ages and warmer intervals. Huge glaciers have advanced and retreated, carving the land and reshaping continents. But why this cycle happens is still debated. Some explanations point to changes in Earth's orbit and tilt, known as Milankovitch cycles, which alter how sunlight is distributed across the planet. Others suggest volcanic eruptions, shifting ocean currents, or feedback loops involving carbon dioxide. Perhaps all of these forces interact in ways we do not yet fully understand. What is clear is that the rhythm of ice and thaw has shaped human history. Our ancestors migrated, adapted, and survived in the shadow of glaciers. Civilizations rose as climates warmed. But the deeper cause, the engine behind these repeating freezes, remains uncertain. Ice ages remind us that Earth's climate is never fixed, but part of a much larger mystery. Mass extinctions can strike suddenly, and their causes remain partly unsettled. 5 times in Earth's history, life has come close to being wiped out. The extinction of the dinosaurs 66 million years ago is the most famous, but even greater catastrophes happened before it, such as the Great Dying about 250 million years ago, when most life on Earth disappeared. Asteroid impacts, supervolcanoes, climate upheaval, and changing oceans have all been proposed as causes. Sometimes the evidence is strong, as with the asteroid impact at the end of the Cretaceous. Other times, the picture is far less clear, with multiple disasters overlapping and producing cascades of collapse. Why do some species vanish while others survive? Why did mammals outlast the asteroid impact while the non-avian dinosaurs did not? Why do some extinctions unfold slowly over ages, while others happen almost instantly in geological terms? Mass extinctions remind us both of life's fragility and of its resilience. Each extinction cleared the way for new forms of life to emerge. But the forces behind these sudden, devastating, and unpredictable events remain only partly understood. Saturn's rings appear surprisingly young, and we do not know exactly how they formed. Saturn's rings are among the most spectacular sights in the solar system. Broad bands of shining ice and dust circling a giant planet. They stretch across hundreds of thousands of kilometers, yet they are astonishingly thin, in some places only a few dozen meters deep. For a long time, scientists assumed the rings were as old as Saturn itself, more than 4 billion years old. But newer evidence suggests something different. The rings look unusually clean, made mostly of bright ice with relatively little dust. If they were truly ancient, they should be much darker, dirtied by micrometeorite impacts over billions of years. Measurements from NASA's Cassini spacecraft suggested the rings may be only a few 100 million years old, a very short time in cosmic terms. If that is true, then how did they form so recently? Perhaps a moon drifted too close and was torn apart by Saturn's gravity. Perhaps comets or asteroids broke up and spread debris into a ring system. But no explanation is certain. Saturn's rings may even be temporary, destined to fall into the planet over the next 100 million years. We may be living in the brief era when Saturn wears this dazzling crown. Their origin remains one of the solar system's most beautiful, unsolved mysteries. Uranus spins on its side, and no one knows for sure why. Among the planets, Uranus is the odd one. Instead of spinning upright like Earth, it seems to roll through space on its side. Its axis is tilted by about 98 degrees, so it rotates almost horizontally. For part of its orbit, one pole points almost directly at the Sun, bathing that hemisphere in decades of light, while the other remains in darkness. How did Uranus end up like this? The leading idea is that long ago, a massive collision with a protoplanet knocked it onto its side. But such an impact might be expected to leave clearer evidence, such as a major moon or obvious scars in its atmosphere. Another theory suggests that multiple smaller impacts gradually tilted the planet over time. Others propose that gravitational interactions with other giant planets early in solar system history slowly pulled Uranus into its strange orientation. Whatever the cause, Uranus remains unique. Its sideways rotation creates bizarre seasons and may also affect its magnetic field, which is itself strangely tilted and offset. No spacecraft has visited Uranus since Voyager 2 in the 1980s, leaving most of its mysteries unresolved. Until we go back, Uranus keeps rolling quietly on its side, carrying a cosmic mystery no other planet seems to share. Venus spins backwards, and its unusual history is still debated. Venus, often called Earth's twin, is close to our planet in both size and mass. But it is also deeply strange. One of its strangest traits is the way it rotates. While most planets spin in the same direction that they orbit the Sun, Venus turns the opposite way. On Venus, the Sun would rise in the west and set in the east. Stranger still, one day on Venus lasts longer than an entire Venusian year. How did this happen? One idea is that Venus was hit by a massive object early in its history, flipping its rotation. Another theory suggests that tidal forces from the Sun slowly reversed its spin over time. A third possibility imagines that Venus once rotated quickly like Earth, but its thick atmosphere and interior dynamics gradually slowed and then reversed that motion. No single theory fully explains the planet we see today. Its atmosphere, dense with carbon dioxide and sulfuric acid, may preserve clues, but for now, Venus keeps its secrets. Beneath its permanent clouds, Venus turns slowly backward, defying expectation and reminding us that even worlds that look familiar can hide the strangest pasts. Neptune is filled with storms we still do not fully understand. At the edge of the solar system, Neptune roars with winds faster than anything on Earth, reaching nearly 2,000 kilometers per hour. Huge storms swirl across its deep blue atmosphere, appearing and disappearing in ways that continue to puzzle scientists. The most famous of them, the Great Dark Spot, was discovered by Voyager 2 in 1989. It was a storm about the size of Earth. But when the Hubble Space Telescope looked again a few years later, it was gone. Other dark spots have appeared since then, moving across the planet, sometimes breaking apart or fading away without warning. Why does Neptune, so distant from the Sun, have such violent weather? Because it receives so little solar energy, the answer is not obvious. Some scientists think Neptune's internal heat powers the storms, while others suggest its atmosphere amplifies small disturbances into giant tempests. But the details remain uncertain. Neptune is still a distant world of storms visited by only one spacecraft. Its mysterious weather shows that even in the cold outer reaches of the solar system, chaos can still rule. Jupiter's Great Red Spot has raged for centuries, and no one knows what its future will be. Ever since humans first turned telescopes toward Jupiter, the Great Red Spot has been visible in its atmosphere. It is a storm so enormous that Earth could fit inside it. It has lasted for at least 350 years, and perhaps much longer. But why it formed, and why it has survived so long, are still mysteries. The storm is an anticyclone spinning counterclockwise in Jupiter's southern hemisphere. Fed by the vast energy of Jupiter's atmosphere, it has seemed almost eternal. And yet, in recent decades, scientists have noticed that it is shrinking. Once wide enough to hold 3 Earths across, it now spans only a little more than one. Some think it may disappear completely within the next century. Why did the storm begin where it did? Why has it survived for centuries when storms on Earth usually last only days or weeks? And if it fades, will it be gone for good, or return in cycles we still do not understand? The Great Red Spot is a cosmic paradox, ancient yet vulnerable, and one of the most famous mysteries in the sky. Comets gather in a distant cloud we have never directly seen. For thousands of years, comets with their glowing tails have fascinated humanity. They sweep in from the far edges of the solar system, curve around the Sun, and then vanish once more into darkness. Astronomers believe these icy wanderers come from a vast reservoir far beyond Pluto called the Oort cloud. The Oort cloud is thought to contain trillions of icy bodies, leftovers from the birth of the solar system. It stretches so far that its outer edge may blend into interstellar space. And yet, even though it is believed to be the source of long-period comets, it has never been observed directly. Its objects are too small, too dim, and too distant. We know of the Oort cloud only through the comets it sends inward, visitors that hint at the enormous unseen population beyond. Was it formed by the scattering of material from the early planets? Does it stretch even farther than we imagine? We still do not know. The Oort cloud remains the great unseen frontier of our solar system, a ghostly shell surrounding us, filled with secrets we have yet to witness. Many moons hide oceans beneath ice, but we do not know what may live there. Beyond Earth, water does not seem to be rare. Moons such as Europa, Enceladus, and Titan conceal oceans beneath frozen crusts. Some of these oceans may contain more water than all the seas on Earth combined. They remain liquid because of tidal heating, where the gravity of giant planets flexes the moon's interiors and generates heat. What makes these hidden oceans so exciting is the possibility of life. On Earth, where there is water, life usually follows. Deep-sea hydrothermal vents on our planet support entire ecosystems without sunlight. Could similar environments exist beneath alien ice? We have clues. Enceladus sends plumes of water into space that are rich in organic molecules. Europa's cracked icy shell suggests active processes below. But we still cannot directly look into these oceans. What kinds of life might exist there? Only simple microbes, or something far more complex? Until we explore those hidden seas, the answer remains buried beneath the ice, waiting in darkness. Enceladus sprays water into space, and we do not know what stirs beneath it. Saturn's small moon. Enceladus may look plain at first glance, just a bright icy sphere. But when NASA's Cassini spacecraft flew past, it found geysers erupting from fractures near the South Pole, blasting water vapor and ice grains far into space. These plumes contained salts, organic compounds, and even signs of chemical reactions that on Earth would suggest a habitable environment. Beneath its surface, Enceladus hides a global ocean warmed by Saturn's tidal pull. The geysers may be openings connecting that ocean to the surface. But what drives those eruptions? Are they powered by hydrothermal vents on the seafloor, like the ones in Earth's oceans that teem with life? Or are they driven by some other unknown process? Enceladus is small, only about 500 kilometers across, yet it has become one of the most promising places to search for life beyond Earth. Its plumes give us a direct sample of its hidden ocean. But until future missions return, the mystery of what moves beneath its ice remains unsolved. Titan has seas of methane, and something keeps refilling them. Titan, Saturn's largest moon, is a world that feels both familiar and alien at the same time. It has lakes and seas, rivers and rain, but they are not made of water. They are made of liquid methane and ethane. Titan's skies are hazy, and its landscape is shaped by weather unlike anything on Earth. Here is the mystery. Methane in Titan's atmosphere should be broken apart by sunlight over time. If that were the whole story, its methane seas should have disappeared long ago, and yet they remain. Something underground, or hidden within Titan's chemistry, seems to be replenishing them. Some scientists suggest cryovolcanoes may be releasing methane from Titan's interior. Others think unknown chemical processes are responsible. Even more intriguingly, methane can also be considered a possible biosignature, a potential sign of life. Could Titan's methane have a biological source? We do not know. Titan's methane cycle mirrors Earth's water cycle in strange and haunting ways. But the source that keeps it going, the hidden engine that refills its seas, remains unsolved. Mars once had flowing rivers, but we still do not know where the water went. Billions of years ago, Mars was a very different place. Huge river valleys carved its surface. Deltas and ancient lakebeds show where water once flowed. The planet may even have held oceans. Today, Mars is cold, dry, and frozen, with only a thin trace of water vapor in its atmosphere. So what happened to all that water? Some of it may be locked away as underground ice. Some may be trapped inside minerals. Much of it may have escaped into space after Mars lost its protective magnetic field. But the full story remains unclear. Mars is covered with signs of its watery past, yet its present is a desert. Did the water vanish gradually, or was it lost in sudden changes? Could liquid water still exist underground today, hidden from view? The fate of Mars's ancient rivers remains one of the greatest mysteries in planetary science. Solving it may help answer whether Mars once supported life and whether it still might. Mathematics describes the universe with astonishing accuracy, yet we do not know why. Mathematics is a language of patterns, a human system built from numbers, symbols, and logic. And yet, remarkably, it describes the universe with extraordinary precision. Equations imagined on paper end up governing stars, atoms, and galaxies. Einstein's equations predicted black holes before anyone observed one. Maxwell's equations described radio waves before they were detected. Why should abstract symbols map onto reality so perfectly? Some scientists argue that mathematics is discovered, not invented, and that it reveals truths already woven into the structure of the cosmos. Others say math is a tool shaped by the human mind, refined through evolution to match the patterns we observe. But neither idea fully explains the eerie success of mathematics in physics. Why should the same equations describe both the arc of a thrown ball and the motion of distant planets? Mathematics is both a human creation and a universal key. Why it works so uncannily well remains one of the deepest mysteries of existence. The constants of nature appear fixed, yet their values remain unexplained. Every law of physics rests on certain constants: the speed of light, the charge of the electron, the strength of gravity. These numbers shape the universe, change them even slightly, and stars might never form. Chemistry might fail. Life itself might become impossible. But why do they have the values they do? Scientists can measure these constants with extraordinary precision, but no theory fully explains why they are exactly what they are. Some say they are simply accidents of this universe. Others imagine a multiverse, a vast collection of universes with different constants, and we just happen to live in one where life is possible. But these remain speculations. The constants of nature are like settings on a cosmic control panel, fixed, exact, and still unexplained. They are the background music of the universe, a tune we can hear clearly but did not write ourselves. We still do not know whether true randomness really exists. Toss a coin, roll dice, shuffle a deck of cards. Randomness feels obvious, but physics makes the issue far stranger. At the quantum level, particles behave in unpredictable ways. An electron may show up here or there. A radioactive atom may decay now or later with no visible cause. Is that genuine randomness or only complexity beyond our present understanding? Einstein famously rejected the idea, saying that God does not play dice with the universe. He believed hidden laws must govern quantum events. But decades of experiments have pointed in another direction. Quantum mechanics may truly be irreducibly random. Even so, some scientists suspect deeper laws still remain to be found. Others think randomness is built into reality itself. If true randomness exists, then uncertainty is not merely a sign of ignorance. It is part of the nature of the universe. Whether reality is fundamentally ordered or truly random remains one of the central unanswered questions in physics. Time itself is still one of science's greatest mysteries. We live inside time. We feel it moving second by second, carrying us from the past toward the future. Yet science still cannot fully explain what time actually is. Einstein showed that time is not absolute. It bends and stretches depending on motion and gravity. A clock high on a mountain runs faster than one at sea level. A clock in orbit ticks differently from one on Earth. Time is woven together with space into a single fabric. But why do we experience it as moving in only one direction? Why does the past seem fixed while the future feels open? Some physicists link the arrow of time to entropy, the tendency for disorder to increase. But that only shifts the question. Why did the universe begin in such an ordered condition? Others suggest time itself may be an illusion, a feature of human perception rather than a basic part of reality. Time governs every heartbeat, every thought, every life. Yet its true nature remains one of the deepest mysteries we face. Matter exists, but antimatter almost vanished, and we do not know why. At the beginning of the universe, the Big Bang should have produced equal amounts of matter and antimatter. But when matter and antimatter meet, they destroy each other in a burst of pure energy. If they had been perfectly balanced, everything should have disappeared in an instant. No stars, no planets, no people. And yet, here we are. Somehow, matter won. Why did matter gain the advantage? Experiments show that matter and antimatter behave almost identically, though with tiny asymmetries. Those small differences may have shifted the balance in the early universe, but they do not appear large enough to explain why anything exists at all. Somewhere in the physics of the early cosmos lies the answer to why there is something instead of nothing. Until that answer is found, the triumph of matter over antimatter remains an unsolved puzzle. Particles have mass, but we still do not fully understand what gives it to them. Everything around us has mass, from stars to grains of sand to our own bodies. But why do particles have mass in the first place? For decades, that was one of the biggest mysteries in physics. The discovery of the Higgs boson in 2012 confirmed that an invisible field fills the universe. As particles move through it, they acquire mass, somewhat like swimmers pushing through water. Without this field, matter as we know it would not exist. But the Higgs mechanism answers only part of the question. Why does the Higgs field itself exist? Why does it have the strength it does? And why do different particles interact with it in such different ways? The discovery of the Higgs opened a door, but behind that door lies a deeper mystery. Mass feels solid and obvious to us, yet its true origin remains partly hidden in the invisible fields of the cosmos. Reality may be continuous, or it may be pixelated. No one knows. To our senses, reality feels smooth. Space seems infinitely divisible, like a line that can be cut forever. But at the smallest scales, the truth may be very different. Some theories suggest the universe is pixelated, built from tiny indivisible units like the pixels on a screen. This smallest scale, known as the Planck length, is far beyond anything we can currently observe, but it may underlie everything. If reality is pixelated, then space and time are not smooth after all, but granular. That would mean the rules of physics need major revision, but so far, no experiment has confirmed such a picture. Whether the universe is continuous or digital remains one of the strangest questions in science. The answer could reveal the true texture of reality itself. There may be a smallest possible length in space, but we have not found it. Physics keeps driving us towards smaller and smaller scales. Atoms, once thought indivisible, were split into protons and electrons. Protons themselves turned out to contain quarks. Yet there may come a point where smaller no longer means anything. This limit is thought to be the Planck length, unimaginably tiny, around 100 billion times smaller than a proton. At that scale, space may no longer remain smooth, but instead become foamy, uncertain, and quantum in nature. But no experiment can probe that realm yet. If space really has a minimum unit, then the universe is not infinitely divisible. Reality would have a bottom floor, the smallest building block of existence. Whether such a limit truly exists remains one of the deepest mysteries in physics. The laws of physics could have been different, but no one knows why they are what they are. The universe runs on laws: gravity, electromagnetism, quantum mechanics. They are elegant, precise, and dependable. But they might have been otherwise. Why this set of laws and not another? Why a universe where stars can form rather than one where matter instantly collapses or drifts apart? Some scientists imagine countless universes, each with its own laws, and ours is simply one where the conditions allow life. Others think deeper principles, still unknown, determine the laws and fix them in place. But for now, the origin of the laws themselves remains unexplained. We can describe the rules. We still cannot explain why these particular rules, and not others, are written into reality. And perhaps the greatest mystery of all is whether we will ever truly understand any of this. Science has already carried us far. We have mapped galaxies, split atoms, decoded DNA, and walked on the moon. Yet every answer reveals more questions. Every discovery opens the door to new mysteries. Perhaps one day we will explain consciousness, the origin of life, the birth of the universe, and the nature of time itself. Or perhaps there will always be questions just beyond our reach, mysteries that cannot be solved because they are woven into the structure of existence. The greatest mystery may not be the universe alone, but our place within it. Whether human minds can ever fully comprehend the whole of reality. As you drift toward sleep, you might hold that thought gently. Curiosity itself is part of the mystery. To wonder is to be human, and to seek is to be alive. The questions may never end, but neither will our search. You have just traveled through 100 of science's greatest mysteries, questions stretching from the cells inside our bodies to the farthest edges of the universe. Each one is a reminder that for all we have discovered, reality remains far deeper, stranger, and more beautiful than we can fully grasp. Think of what we have touched tonight: the hidden spark of consciousness, the riddles of memory and aging, the secrets carried by oceans beneath icy moons, the timeless puzzles of stars, storms, and the very fabric of reality. Some of these questions may be answered in your lifetime. Others may remain mysteries for generations, and some may never be solved at all. But that too is part of the wonder. To live in a universe that still contains so much unknown is to live in a universe filled with possibility. Every unanswered question is an open door. Every mystery is an invitation. The fact that we do not yet know keeps science alive, keeps curiosity burning, and keeps us leaning toward tomorrow. And as you lie here now, letting the weight of these mysteries drift across your mind, notice how gently they draw you toward rest. Like the slow rhythm of waves on a shore, the questions themselves can be soothing. They do not need answers tonight. They only need to be carried, like starlight across a dark sky. So let your breathing settle into rhythm. Let your body grow heavy and your thoughts soften. Imagine yourself floating through the mysteries we have explored, passing among them like constellations in the night. Questions above you, questions below, a whole galaxy of wonder surrounding you, and you at the quiet center, resting in the knowledge that mystery is not something to fear, but something to welcome. If you are still awake, you can watch the next video whenever you are ready. But for now, there is nothing left to do, no answers to chase, no puzzles to solve, only the calm certainty that mystery itself can be a kind of lullaby, carrying you into sleep. Good night, and may your dreams be filled with sweet wonder.